All right, so I believe last class we ended with, let me pull this up here real quick because we were monkeying around with stuff before class started here, even though to no avail once again. Oh, I know where it's at. I just got it sitting over here. So we went through weighted means, weighted variances. If I remember right, we did some percentile stuff, and we kind of stopped with these percentiles, right? And I said I'll kind of show you something next class. So yet again, we don't have this dot cam, so I'm gonna wing this, but I think I have an idea of how to show this to everybody. So we talked last class about this idea of interpolation and kind of how we find these different percentiles, right? So let's assume that I found the 75th, the 50th, and the 25th percentile. So we talked about this, how we would find those values. So let's say I then use this to find the 25th, 50th, and 75th percentile. What we would call these are our quartiles, okay? So these quartiles, right, we can use to come up with something that you might see in other classes, which is called like a box and whiskers plot, right? So this box and whiskers plot is going to allow us to identify if we have any outliers or any data points that are so extreme that we might want to reconsider kind of using them in calculating some of our different statistics. So have these in mind. This is just the 25th, 50th, and 75th percentile. Now notice that that second percentile, or like the 50th, also represents the median, right? Because we said the median is the value that is greater than 50% of the observations, but also less than 50% of the observations, which is exactly the definition of the 50th percentile. So those two things are the same, right? So we're going to use that first and third quartile to come up with something called the interquartile range, or kind of here I'm just calling it IQR. I'll then go and start with my first quartile value, go 1.5 times the interquartile range below it. I'll call that my lower limit. 1.5 times my interquartile range above the third quartile, call that my upper limit. Right, so I'll give you a kind of a drawing of this here. Maybe I gotta do a blank slide here. I'm gonna try to use this annotate tool. So let's say I start out, right, and I plot. All I do is I plot wherever my second quartile is, or my median, and let's just say that value is 50, okay? So I plot this line at 50. If I think about kind of have like this imaginary y-axis here. The next thing I'm gonna do is draw a box around that. Let's try to get this to scale here. Down here, the bottom of the box will be my first quartile. And let's say that value just happens to be 40 in this example. And then up here, I'm going to plot my third quartile. And let's say that value ends up being 70. Okay? So I'm just plotting kind of lines almost at my first, my second, and my third quartile. So right away, this gives me a little bit of an idea about the distribution of the data. Kind of notice that 25th percentile is much closer to the median than the third is. So kind of think about here, we might, if we were to draw this out as a kind of distribution, we'd have a longer right tail here. Right? We then go, what do we do here? Let's draw just a line. We then draw a line that goes up from this third quartile, and we plot the top of it where the third quartile plus 1.5 times that interquartile range. Okay? Now, if I do this math, what's my interquartile range here? 30 times 1.5 would be 45. Add that to my third quartile, 70 plus 45. So I'd be at, what, 115 up here? And usually the way you'll see it, it's a straight line and they put like a little kind of T on the top of it like that. Okay? I then go down to my first quartile and I draw a line that goes down. We'll draw a little T on that one as well. And I plot that at, take my first quartile value and subtract 1.5 times that interquartile range, which once again, the interquartile range, just the difference between the third and the first quartile. So the difference was 30 there, times 1.5 is 45, 40 minus 45 would be what? -5. Okay. So I've created my lower limit and my upper limit based off of kind of these quartiles that I calculated, or these different percentiles, right? The third quartile being the 75th percent, the first quartile being the 25th. Now I can think about if I was able to observe, let me see if they've got just where I can make a bunch of dots. I think maybe this is. If I can observe all the data points, right? I'm then just going to think about, I could plot them. So maybe there's one data point that is 52, and there's one here that is 45, and then there's one here that's 63, and there's another one that's 60. And I start plotting all these different observations that I see in my data set, right? Just plotting them. If I ever end up with one that is outside kind of my upper or my, my lower or my upper limit, these points that would be outside of that upper and lower limit, we would say those are outliers. Oops. Okay, so if they're above that upper and lower limit, we can use this and we say this is the Q test. If they're outside of that upper and lower limit, we can consider those observations outliers, and we can actually, when computing things like the mean, we can actually disregard those, right? They vary so much from the majority of the data that there must be something weird going on with those observations. Either they were misrecorded, it's just one person who had a very different response, you know, to whatever policy I'm looking at than the majority of people, and so we're gonna ignore those observations, right? So this is called the Q test. You might see this, like I said, in different courses. I know marketing that has a little bit less data. They like to use a lot more of these box and whisker plots. I won't probably have you do a whole lot with them on the homeworks, but I did want to introduce the idea since we had talked about percentiles, and since I know you probably might see them in other courses, okay? Any questions on this before we keep moving? Pull the chat up here. So, okay with this? All right. Really okay, because I'm going to clear it here. All right. So, if we go back here, this is always a good meme, right? Anything outside we consider an outlier. So please don't reject me as an outlier because you were the Q test, right? Because the Q test is what rejects outliers. So that's a nice, fun meme there. I don't know why it did that. Anyways, so that kind of picks up where we left off. Just like with tables and graphs, we were really focused on one variable, and now we're going to look at, well, what if we want to know about the relationship between two variables? With graphs, we said we could do a scatter plot, right? I showed you how to do one of those in Excel. But we also, you know, can think about what we're trying to get with that scatter plot. We were trying to understand that if the X variable goes up, what do we tend to see the Y variable do? Does it also go up? Does it go down? Or not do much of anything, right? Or does it change at all? So we have two measures to capture this, what the relationship is between two different variables. So the first is called the covariance. Once we know how to calculate the covariance, we can use that to calculate something that's a little bit more useful, which is called the correlation coefficient, or you might have heard this before, just talked about as a correlation. All right. So the setup is we have these two variables, and we want to know the relationship between them. So X and Y, I'm going to show you some data eventually where it's height and weight, so I'll probably just talk about it as though the two variables we're interested in are height and weight. What's the correlation, or what's the relationship between those two variables? Now, intuitively, we can probably think before even looking at the data, well, if I'm looking at someone who's 5 feet tall relative to 7 feet tall, the person who's 7 feet tall, I hope, weighs a little bit more, right? So we think there's probably going to be a positive relationship, but how can we use data to quantify that? Okay? Because it's not necessarily that, you know, just because someone's an inch or two taller than someone else that they are going to weigh more. So we'll write that population covariance. So if we have population data, the covariance would be written as sigma. But then, unlike the standard deviation where we just used one variable there to identify this is the variant, or sorry, this is the standard deviation of X. When we write sigma and then two variables, X and Y here, that signals that this is a covariance measure. Okay? The notation is not perfect. You know, for me, for writing the variance as sigma squared, it makes a little more sense to write the covariance as sigma squared and then XY, but this is the notation. Okay? So what we're going to do is go through every observation, and let's say we had a list of people and we had their height and weight. We take the very first person and we'd say, okay, what's the difference between their height and the average height? Take that difference and multiply it by the difference for that first person between their weight and the average weight, right? So what this is essentially capturing is, you know, on what side of the average does this observation's two variables lie, right? Are they above average height and above average weight? Are they above average height but below average weight, below average height, above average weight, or are they both below the average, right? Once we do that for every observation, we add them all up. So it's almost like every observation is going to influence this covariance a little bit. So one observation might be evidence that height and weight tend to be on the same side of the average, right? Another observation might be evidence that they tend to be on different sides of the average, okay? But once we look at every single observation and then divide by the number of observations, this covariance should be a measure. You can kind of think about it as the average relationship that we tend to see between this X and Y variable, right? Or on average, do we tend to see this X and Y variable be on the same side of the average, both above the average, or do we tend to see them on different sides, one below the average and the other above? Okay. And we'll look at some data, but this is, you know, kind of trying to think about the mathematical formula, how we start thinking about this. So we also have the sample covariance. Everything's the same. It's just instead of divided by n, we divide by n minus 1. So very similar to the variance there. That's not anything wildly new. All right. So what does the covariance mean? Well, I kind of already described the definition, but really, we can just look at the sign. If this is positive, that's telling me that X and Y tend to move in the same direction. As X goes up, Y goes up as well. Or as X is higher, Y tends to be higher as well. If it's negative, that's telling me that as X is higher, we tend to see Y be lower. And then if it's almost 0, what we're really saying is there's no relationship. As X changes, Y doesn't change at all, okay? So this is kind of, the sign of the covariance will be very useful to us. So if I had a data set with, you know, I think I grabbed this from the CDC, so 44,000 people, and I have their height and weight, the procedure would be, okay, first, calculate the average height, right? If I had a column in Excel, this would be very easy, right? Equals average, select the entire column. That's actually exactly what I did. And I get the average height from this sample. I then could find the average weight doing the same thing. So I've got my mean height and my mean weight. So I'll go to the first observation and I'll take the difference between that person's height and the average height. I know these aren't showing up real great here, but there is like supposed to be like a bar above this X and Y. For some reason, it kind of truncated, just made it small here. So I'll take their height, subtract the average height. You gotta be kidding. All right, so this person is above average height, right? However, they are below the average weight. So when I look at the difference between their height and the average, it's a positive value because they're above average height. However, they were below average weight. So this one observation, when I multiply these two differences by each other, positive times a negative is a negative. If they're on different sides of the average, if height and weight are on different sides of the average, I'll end up with a negative value here because that would be an observation that said, well, look, this person was taller than average, however, their weight was below the average. That's evidence that these two things kind of move in opposite directions, right? There's an inverse relationship. Now, that was one observation, right? So that one observation adds a negative value to my covariance because it was evidence that there's there's an inverse relationship between those two variables. But that's just one observation, right? That could be true for one observation, but if the rest of the 44,000 observations show me the opposite, well, that's, I have to take that into consideration. So I go through, and for these next three people, this person just barely, but they're all below the average height, and their weights are below the average weight. So notice the difference will be negative, right? Negative times a negative. Each one of those observations is evidence, right, that these two variables tend to be on the same side of the average. When someone's below average height, we see that they are below average weight as well, right? So you can kind of think about, there's 44,000 observations here, but yeah, this one observation was evidence that these two variables might have an inverse relationship. But the next three were evidence that they have a kind of positive or a direct relationship. As x goes up, so y, as x is higher, y tends to be higher as well. So once we have this for every observation, we'll add them all up. And every time we get evidence that there's a positive relationship between these two variables, it outweighs these observations that provided evidence that there's a negative relationship. And kind of whichever one wins out, when we add them all up, well, that's going to be what we say kind of the average evidence is for what the relationship is between this x and y variable. Okay. Any questions on kind of any of this before we kind of keep moving here? Okay with this? So this is kind of the procedure. Like I said, we'd have to do this for 44,000 observations. But you can imagine, if I had this set up okay for one in Excel, I could like use that double click thing where it just copies it all the way down for the rest of the data set, and it'd be pretty quick to do this. Okay? There's probably also a built-in function for it, but either way, it's pretty easy. Okay? So if I go ahead and I do that for that height weight data, I get this covariance of 76. Okay? So this is where I want to focus a little bit more because there are built-in functions. I'm not as concerned with the kind of computation of the covariance. That's important that we know how to do that. But once we have it, what do we do with it? Right? Okay, so 76 is my covariance. Is that good or bad? Is that a strong relationship between height and weight? Is that a weak relationship? Like, where do covariances usually fall? Can I see a covariance of 10,000? Well, part of the problem is, what are even the units of this measure? Height was in inches, weight was in pounds. If I'm multiplying these two variables by each other, I actually have inch pounds. I don't know what the hell that is, right? So I mean, even the units don't make sense, right? If I was looking at the relationship between years of education and income, year dollars, right? So it has this kind of goofy unit interpretation. And I'm really not sure how to think about the size of it, because when I'm looking for the difference between the average, if I'm looking at height and weight, I mean, I don't know, even if the average height was 5 foot and I see someone who's 7 feet tall, it's only 24 inches, right? That difference would only be 24 inches. While if I'm looking at income, right, if the average income is 50,000, it's very likely I see someone having an income of 60,000, and that difference is 10,000, right? So just the original kind of variation I see in the original variable is going to influence what the size of my covariance could be. Because with height, I can't see a difference of 10,000. Right, 10,000 inches. That doesn't even make sense. But with income, it's very likely I could. So we've got a problem with our units, and we have a problem that this scale is going to be way off depending on which two variables we're looking at. Right? I can't compare the relationship between height and weight to the relationship between years of education and income. But I want to do things like that. So what do I do? Right? So we've got this problem. We don't really know how to interpret the covariance. So what we're going to do is use that covariance. And I said we were concerned with the fact that the original variation in the variable, right, whether or not it was income or height we're looking at, is going to influence the size of the covariance we could see. So what we're going to do is take that covariance between these two variables and divide by the standard deviation of each variable. Okay? So I thought we'd have a dot cam, and I was going to give you a loose idea about why this is. I'll try to return to that Tuesday just to mention it. I wasn't going to give you the pure mathematical proof, but you can kind of imagine, right? In my covariance, I've got the difference for the x variable from its mean and the difference for the y variable from its mean. Well, in my standard deviations, I also had that deviation from the mean. Now it was being squared, but then I took the square root. So you can kind of imagine how there's similar components in the covariance and in the and in the standard deviations of these variables. But all you need to know is that when we divide by the standard deviations of each variable, what we're doing to that covariance is we're essentially kind of taking out the original variance of those variables so that we're scaling it so that now everything is kind of apples to apples comparison. We've accounted for the original variation that existed in the x and y variable, so that when we do this, our correlation coefficient always ends up being between 1 and -1. 1 would be a perfect positive correlation between these two variables. Think about it as, as height goes up by 1 unit, weight would go up by 1 unit as well, so 1 inch and then 1 pound there. Okay? And then as years of education went up by 1 year, we see kind of income go up by exactly 1 unit as well, right? However we're measuring it. But the other nice thing that we've done here is, remember I said the covariance when we had height and weight would be like inch pounds. Well, think about, so we have inch times pounds in the numerator. We have inch times pounds in the denominator. That would cancel. It's a unitless measure as well. So not only do we get it to be between 1 and -1, but we strip the units. So now we can compare the correlation coefficients for height and weight to the correlation coefficients for years of education and income. Okay? Now, the way that we write the population correlation coefficient, we'll use this Greek letter rho, and then for the sample, we use R. And the only difference there is, right, if I have population data, I'm using a population covariance and population standard deviation. If I want only have sample data, I'm using the sample covariance and the sample standard deviations. Right? There's no kind of difference though, and we're just plugging these values in once we find them. So same kind of thing holds as the covariance though. The sign of our correlation coefficient still tells us something about the relationship between these two variables. So if it's negative, that means that as x goes up, y tends to go down. If it was a positive value, it means as x goes up, y tends to go up. And if it's 0, as x goes up, y doesn't change at all. Okay? So the same kind of ranges apply to this correlation coefficient, but it's now unitless and scaled so we can compare across relationships. Okay? So if we use this equation and we go back, I can actually compute, I have that covariance between height and weight. I can very easily in Excel, with those two variables, find the sample standard deviation of each variable. And now it's just a matter of plugging values in, right? My covariance is 76, my standard deviation is about 4 here, and my other standard deviation is 43. And now it's a pretty simple thing to enter into my calculator. Okay? 76 divided by 4, and you could then divide by 43. Any questions on that? Once we have these 3 measures, it's pretty easy to find that correlation coefficient. So if we do that, we get about 0.45. So is this a strong relationship? Is it not? Well, I mean, if we think about our correlation coefficient has to be between 1 and -1. So 1 would be the strongest positive relationship I could see. I see 0.45. Well, 0 is no relationship. 1 is the strongest. We're kind of right in the middle, right? It's not the strongest relationship, but it's not the weakest either, right? And with this 0.45, we can now compare to other types of relationships. So let's say I have years of education and income. I go ahead, calculate the covariance, calculate the standard deviations for each variable, plug them into this correlation coefficient equation, and I get 0.73, right? So the correlation coefficient between years of education and income is 0.73. What I could say then is that the relationship between education and income, years of education and income, would be stronger than the relationship that exists between height and weight. Right? Now they're both positively correlated, but the one that has the higher correlation coefficient, that's evidence there's a stronger relationship between those two variables. Okay? Now what's high here? Usually, if you're like, you might get into this in some of your upper level courses, if you start dealing with correlation coefficients, you'd like to see something 0.7, 0.8 or higher, right? This is a pretty, like I said, it's not the weakest, but it's not a very strong relationship, okay? And we can think about really what we're trying to measure here. If I had that scatter plot between height and weight, I could draw like this line of best fit, right? And kind of that slope, when you think about the slope of that line of best fit is really similar to what we're thinking about with this correlation coefficient, right? Now, if I look at this, it looks pretty clear there's probably a positive relationship, but it's not like it's a super steep slope, right? So it isn't like it's the strongest, and that's probably why we end up with about 0.45 as our correlation coefficient. There is a positive relationship here, but it's not very strong, okay? I have a couple other examples here, and this might kind of be some that you could kind of make sure that you understand this, but it's pretty easy. Right? Like once I give you the covariance and the 2 standard deviations, all you're doing is taking that covariance and dividing it by each of those standard deviations. So 330 divided by 8, and then divide by 48 would give you your correlation coefficient. Now, if I'm looking here, which of these can I rule out right away? One of them I can rule out really easily, hopefully. The negative one, why can I rule out the negative answer? Who said it over there? So, right, the standard deviations, remember variances are always positive. So when I take the square root of a positive value, my standard deviations will also always be positive. But if my covariance is positive, that tells me my correlation coefficient will be, right? Because, go back to this equation, we know the denominator, these values will always be positive. So the sign of my covariance tells me the sign of my correlation coefficient. So if my covariance is positive here, I can't have a negative correlation coefficient. So I know it has to be one of these. I can rule one of these answers out as well. What was the whole point we were doing? We were finding this correlation coefficient. We wanted to be able to compare across different types of relationships. So we said that this correlation coefficient is within what range? -1 and 1. So this is clearly outside that range, right? 1969 is way outside. So if I'm just throwing darts here, A or C seems like that one of those has to be the right answer. Now from there, you just actually have to do the computation, divide that covariance by each standard deviation. Same kind of idea here. Let's say I'm looking at, and I don't know, I don't think we'll watch it today. I might just give you the link and tell you if you want a good laugh to watch it on your own. We'll see what happens with time. But there's this economist, and he was trying to look at the relationship between kind of income or wages and kind of someone's looks. So he was calling this beauty in his paper. But let's say we find the covariance and then we find the two standard deviations. What do we know the correlation coefficient has to be? Well, if we find a positive covariance here, we can automatically rule out negative correlation coefficients. We also know it has to be between 1 and -1, so we could rule A out as well. So once again, a large part of the exams will be multiple choice, and so I go through things like this where you start to develop the skills to I'm obviously on one question not going to allow you to cancel out every answer so there's only one left and you don't have to do any computation. But I can't teach you computation in the sense it's easy to make a mistake on a calculator, right? Or it's easy to forget a parenthesis. But I'm really concerned with you understanding the principles. So the fact that you can rule out anything outside the range of -1 and 1, that's important, right? Knowing what this statistic, what range you could even see it in, because once you get down to it, you're going to be using Excel to black box a lot of things for you where you don't see the intermediate steps. But if you, for some reason, enter something wrong into Excel, I want you to be able to identify clearly incorrect answers, clearly I made a mistake somewhere, right? So we can rule out A, we can rule out D. From there, it's just a matter of doing the math. 0.18 divided by 0.68 divided by 4.66. Okay? If you do that, you should get that 0.06. So if you're really concerned with doing this on your calculator, a little bit of practice here, you could work on these two. Might see a very similar question on today's online quiz, right? I'll give you a covariance and some standard deviations. I then ask you to calculate a correlation coefficient, okay? Any questions on that? I know I went through that a little bit fast, but we're okay with this? All right. So this is the link. It's a Jon Stewart clip. Like I said, if we have time at the end, I'll watch it. But it's kind of talking about the relationship between two variables, and also just kind of showing you how crazy some economists can be. So kind of what they go over there is he was trying to look at the correlation essentially between someone's looks and kind of, I think he was focused on wages, but they ended up doing some interesting experiments where it was just in general workforce statistics. So they had, this is a pretty cool study actually. They had people, and I forget the process for which they ranked their attractiveness. I think they got some random people to look at pictures and then kind of rank this group of applicants based on their attractiveness and then put them into these different percentiles, right? Out of all these applicants, where did this person rank percentile-wise in attractiveness, from these random people who were judging them, which just doesn't sound great. But it's interesting because once they have that, they created identical resumes for all these 100 different people they had who were ranked in terms of attractiveness. They sent that same resume out, and there was some part of this component where it was done through LinkedIn. So to get the resume, they had to see the person's profile photo, right? So they know what the person looks like, and they have this resume. but every single person, no matter what their kind of attractiveness, had the same resume. And what they found was kind of the correlation between attractiveness and the number of interview requests that somebody got was actually positively correlated for women. You can see this, like the kind of increase in the percentile. There was an increase in the number of interviews requested. But they found a positive for men as well, but clearly not near as strong, right? That correlation coefficient was positive for both men and women between attractiveness and the number of interviews requested, but kind of it was a stronger correlation coefficient for women, right? So even just this one basic simple statistic allows us to start to look for maybe some possible, right? This shouldn't exist, right? So, and we have differences across genders. So this, you know, these statistics are telling us like, this is a problem. Like here's evidence, here's some statistical evidence that this is an issue. Now we need to figure out policies that can correct it or something like that. So I don't know, I thought that was kind of interesting. I always like to bring it up there. Any questions on any of that before we like really switch gears into the next topic? Okay, so that up to that point, that should be all the material that you could see on that first Connect assignment. I think the very last question has some covariance or correlation coefficient stuff on it. So that's kind of where that first Connect assignment will stop, right? Yeah. So I'll tell you, I have that set at 3 attempts for one reason. Sometimes people accidentally hit the submit button, or they or it times them. I don't know. I've had some issues with some people. Sometimes it submits something even though they weren't done. But there's a tool on there called Check My Work, and I always have it turned on. So basically, you should just take one attempt. You should, because you can keep guessing, and that's not an attempt, right? When you write it in and then check my answer. Yeah, so usually you should only have one attempt because you can save whatever work you have done, and you can use that check my answer tool to, you know, try to take multiple guesses. The only reason I have it set to 3 submissions is, like I said, sometimes something will happen to where it gets submitted. And so instead of me having to go in and, you know, put an extension or, you know, give one student an additional attempt, there's 3 there. So if that happens, you can just kind of pick up on the second attempt where you would leave off. And then I like manually, like, let's say you do the first 5, if for some reason submits, you accidentally hit the submit button, I don't know, the internet ghosts decide to submit it for you. Well, then you can just start your next second attempt at question 6. And then I can go back in and kind of match the two together to give you your total. Does that make sense? Yeah. Okay. Any other questions before we keep going? And then the Excel file should have kind of been up to last class what we were talking about. It's really mainly focusing on how you build a histogram, right? There's some things where you calculate means or variances in there, but those are just those kind of easy built-in functions. So we're definitely covered all the material for those first 2 homeworks, which are due next Friday by the end of the day, okay? Any other questions? Make sure to check the Zoom chat here. All right. So the next thing we're going to talk about, and I'll likely put up, when I get back to my office today, it might take a little bit longer, but sometime this afternoon, I'll put up the next Learn Smart, right? And I'll probably set the due date for that to be the end of the day Wednesday. So we'll be talking about probability, but I'll have that Learn Smart focus a little bit later on kind of the last topics of probability we're going to look at. So if you can kind of get on, make sure you get that done by next Wednesday. Once again, it should be 10 minutes of kind of just going through that material, kind of prepping your mind for what we're going to talk about. Okay? So that topic that we're going to start talking about, if I can get this going, is probability, right? So, you know, when we think about probability, the way we use our words is often talking about probability with actually saying the word. So what are the chances that sales will increase or decrease, right? Or what's the odds that a new investment becomes profitable? Or what's the likelihood that a new assembly method is going to change production? So we're thinking about, you know, all these terms are kind of interchangeable for, we want to get an idea about how likely it is for something to occur, right? Probability is telling us how likely it is something's going to occur. Okay? So these are just all different ways of kind of saying that same thing. So what we're going to do with probability, the kind of setup we need, is that we have some experiment that we're running, right? Where we don't know the outcome of this experiment. Now, when I say experiment, This is not like, shouldn't be thinking physics or biology. An experiment could be me asking you, I don't know, how old you are, what your age is, right? I don't know what the outcome is, right? If I ask a random person what their age is, I know that I have like a certain set of possible responses, right? You could say anywhere between 0 and, I don't know, 100 something, whoever the oldest person is. But I don't know what you're going to respond with. I know based off of like some data maybe that the likelihood of you saying that you're 110 is lower than you saying that you're 22 or something, but I don't really know what the outcome is going to be yet. Okay? So once we have this experiment, we want to make sure we run it in the exact same way several times. So if I was to ask a person what their age is, that's the experiment. I then want to just keep asking that same question to different people. Right? So the possible outcomes I could see, right, we're going to call the experimental outcomes. So the way that I described the age example, seeing any age between 0 and 100 and, I don't know, 20, right, that's my experimental outcomes. I could see any of those as a possible response, right? Or let's say let's do an easier one. I ask somebody what their eye color is, right? I have a certain number of experimental outcomes I could see as a response, right? Green, blue, brown, I don't know. You could probably create some more categories, but you get the idea, right? We'd have kind of a smaller set of experimental outcomes we could see. Okay? Now the sample space, right, is going to be the outcomes that we observe. So going into an experiment, you know what the possible experimental outcomes are that you could see. However, when you actually perform the experiment, maybe you don't see all of those possible outcomes, right? So let's say I'm asking someone what their weight is, right? I know that there's a certain range of experimental outcomes that I could see, right? I don't know, take the lowest person's weight up to the highest person's. I could see any value in between there. But if I ask 50 people, my sample space is going to be, I only see 50, at most 50 different responses for the value of weight, right? So my sample space is going to be a smaller subset of those possible experimental outcomes. Now, the fewer number of experimental outcomes I have, the more likely my sample space could be exactly the same as my experimental outcome. So think about if I'm rolling a die, right? I roll, not a Dungeons and Dragons, right? So we have 6 sides, right? It's just 1 through 6. It's nice and easy. So I roll it, I see a 1. I roll it again, I see a 4, right? You can kind of imagine there's only 6 possible values I could see. If I roll that dice 50 times, I'm going to see every single, I'm going to see 1, 2, 3, 4, 5, and 6 at some point. So in that scenario, because my number of experimental outcomes is low, and I'm running this experiment a higher number of times, my sample space could end up being the exact same as my experimental outcomes. However, if I'm rolling a dice and I only roll it twice, my sample space, I'm only at most going to be able to see 2 out of the possible 6 numbers, right? So, the sample space could be as large as the number of experimental outcomes, but it could be, especially if we don't run this experiment a lot of times, it's going to be a little bit smaller. And then an event is going to be an even smaller subset of the possible outcomes that we see. So an event is, we're going to define the event. So maybe I'm rolling a dice, and I know all the different outcomes, and maybe I'm rolling it 50 times. But maybe the event I'm interested in is how likely is it, if I roll a dice, how likely is it that I see a 2? The event that I've defined is seeing the outcome of 2. I could also define the event of, well, what's the probability that I roll a 2 or a 3, right? Now I've defined the event as seeing either a 2 or a 3, right? So these events are going to look different depending on the example that we're talking about, but they still have to be a subset, right? Some of the outcomes that I could see in my sample space. Okay? So I always kind of give this nice little visual, right? Here's all of our experimental outcomes. It could be anywhere in this circle. Maybe we run this experiment 20 times, and I don't see every single outcome, but I see the majority of them in my sample space. So I know kind of the majority of outcomes that exist. I see those after I run the experiment. I then define an event, which is an even smaller kind of subset of the possible, or the possible outcomes I see, or even the outcomes that I saw in my sample space. So kind of this is like from size of largest to smallest. Okay. All right. You know, so if we think about different experiments, we've got flipping a coin, rolling a die, choosing a card from a deck, playing a football game. I think here, we'll think playoff football game, right? We're getting close to the Super Bowl here. And then playing a soccer game, kind of regular season. So what are my possible outcomes if I flip a coin? I can only see two possible experimental outcomes, which would be heads and tails. Right? That one's pretty easy. If I roll a die, a regular six-sided die, I can see 1, 2, 3, 4, 5, or 6. Right? Choosing a card from a deck. Now this one gets interesting because I could define this two ways, right? I could just see ace through king, right? Or I could even define this as ace of spades, ace of diamonds, right? I could kind of combine the suit and the card number. So here I just kind of had it as though, you know, if I'm just worried about what the card is and not its suit, right, ace through king would be the possible experimental outcomes I could see. Playing a football game, kind of I said in the playoffs here, we just have like win-lose. And then if you have a regular season soccer game, it's much more likely we have kind of this third option, which is tie, right? So these experiments can take on various different forms. To start out, I'm probably going to use this coin and dice one a lot just because like it's something most people are familiar with, and it's I don't know, makes it a little bit easier to understand what we're doing, right? And then we kind of move on to more complicated examples, okay? Any questions up to this point? Probably okay here. Okay? So what we're going to do is we're going to take all these possible experimental outcomes, and we want to start to assign probabilities to each one of those possible outcomes, okay? So we have all these experimental outcomes, and we want to know how likely is it that we see each one of these outcomes, okay? So the probability of an event, right, if we define an event, what's the probability I roll a 2, right? That one's well, we'll do the coin one, right? It's a little bit easier. What's the probability, right? If I flip a coin, what's the probability it comes up heads? Or what's the percent of the time it comes up heads? 50%, so a probability of 0.5, right? Probabilities, right, are kind of like proportions, right, or it's the decimal form of a percentage. So the probability it comes up heads is 0.5, but if I define the event as what's the probability that it comes up heads or tails, well there, the probability it's heads is 0.5, the probability it comes up tails is 0.5, so the probability it comes up heads or tails, if that's how I define the event, it's just the sum of those two, which the probability it comes up heads or tails, those are the only two outcomes, has to be a probability of 1. Sure enough, 0.5 plus 0.5 is 1. Right? Or think about if we want to do the dice example, what's the probability it comes up 1? Well, there's 6 outcomes, all equally as likely, so 1/6. I don't know what that ends up being. So what, 0.1666 repeated maybe? Then I can think about, well, if I define the event as the probability I see a 1 or a 2 or a 3 or a 4 or a 5 or a 6, well, if each one is 1/6, has a probability of 1/6 of occurring, and I define the event that way, it's just add up all those probabilities. 1/6 added up 6 times would just be 1, right? I have to see one of the values. So the probability of an event is just the sum of, the probabilities of the different outcomes within that event. Okay? So now we'll get into a little bit more notation and some rules that we know have to be true about these probabilities. Okay? So we're going to have some experimental outcome that we're interested in, just one experimental outcome. We'll write the probability of that outcome. That's how we write the probability, right? The probability that we see this outcome E occur. Okay? So some of the things that we know have to be true. First, if it's a probability, right? So we can think about this as a proportion. The lowest it can ever be is 0. The lowest the probability of something can occur, like let's say what's the probability, I don't know, a dragon bursts into the room right now? Well, it's impossible that's going to happen, but you can't have a negative chance of something occurring, right? At the very least, it just has a 0% likelihood that it occurs, or a probability of 0. So that's the lowest it can be. The highest it can be, if it's a sure thing, we say, well, the chances it would occur is 100%. Well, the probability then, we can think about, we're moving that decimal 2 places, the probability would just be 1, right? So the highest we could ever see, like a sure thing, would be a probability of 1, and something that we know can't happen would have a probability of occurring of 0, okay? So we know that it has to be within that range. We also know if we look at every single possible outcome, if we add up the probabilities of every possible outcome, those have to add up to 1. So this is very similar to the idea that when we were looking at, say, building a histogram, right? If I've looked at, or when we were doing the qualitative data where we had like the different car colors, if I've looked at every single possible car color, when I took those relative frequencies, I said those relative frequencies really represent proportions, or kind of we can think about them as probabilities. So those relative frequencies had to add up to 1, because if I've accounted for every single possible outcome, and I say, well, what's the probability that all of them, that at least one of them has occurred? We went back here, we said the probability of that event would just be add up the probability of every possible outcome. If I add all those up, I have to get to 1. Right? I have the proportion, you know, if I use the dice example, what's the probability I roll 1, 2, 3, 4, or 5, or 6? Well, that's every possible outcome. If I add those probabilities up, I have to see one of them, so the probability is 1. Okay? So if I add the probabilities up of every possible outcome, we get 1, and that'll kind of help us with some of the stuff we're going to do in a little bit. Okay? Any questions here? Okay. So there's a couple different ways we can think about assigning probabilities. In this class, we're really going to focus on one, but I'll introduce the other two to you as well. So we've got the classical method, the empirical method, and the subjective method. So this is kind of a summary of the three, and I'll dive in a little bit more into each one. So the classical method, right, is really the easy examples, right? It's going to be where we know that each outcome is equally likely to occur. So flipping a coin, the two possible outcomes are both equally as likely to occur. So we said if there was two outcomes, the probability that each one would have would be 0.5 or 1/2. If I think about rolling a dice, right? There's 6 different outcomes. The probability that each outcome occurs is 1/6, right? If I had, I'm pulling a card out of a deck, and there's what, ace through king, so 13 different types of cards I could see. If I ignore the suit, then the probability that I pull a king out would be 1/13, right? So the way that we assign the probabilities using the classical method would just be 1/, right, the number of possible outcomes, right? Or I could think about it here. Oops, let me write this. I think I can maybe write this. So we just do 1/n, right, where n represents the number of possible outcomes I could see. That's how we assign probabilities using the classical method. So let's say instead of flipping a coin once, I flip it twice. What are the possible outcomes I could see? Well, I could get a heads, then a heads. I could get a heads and a tails. I could first get a tails and a heads, or I could get 2 tails. 4 different possible combinations I could see for the outcomes for flipping a coin twice. Each one is equally as likely to occur. So I would say the probability of any one of these being the outcome I see is 1/4, right? Or 1/n. Just n here, there's only 4 possible outcomes. Okay? Any questions on that one? That one's pretty easy, and we use it, in these cases where it's like flipping a coin, rolling a dice, pulling a card out of a deck. When we start to think about things like survey questions, if I said, what's the probability that someone has, I don't know, blue eyes? Well, it's not going to be 1/, the number of possible eye colors I could see, right? We know certain eye colors are more likely to occur than others. So there's only a limited number of times we can actually apply this classical method. Okay, so clear this, we'll keep going. So the next one, which is going to be the one we focus on and is the most likely to be used, is the empirical method. Okay? So the empirical method is we're going to look at a bunch of data, right, where this experiment has been performed many times, right? So, This experiment has been repeated many, many times. We've seen the outcomes that can occur. So if this is like rolling a, well, let's say, I don't know. Let's say I have a 6-sided dice, but I don't know what the pictures are on it. But I roll that dice 1,000 times. I now know what the pictures are. And I know which ones are actually more likely for me to see. Maybe it's not, maybe it's a weighted dice, right? Well, I can figure that out based off of looking at the data, looking at the outcomes of those first 1,000 rolls that I had. So another kind of example that I always use is like a lot of times we look at survey questions. So let's say I ask, I don't know, a class of 60 what their favorite cuisine is, and they all give me their responses. 15 of the 60 responded that Mexican food is their kind of favorite cuisine. And so I say, okay, so what's the probability if I asked a student at random that their response would be that Mexican food is their favorite, right? Well, based off the data, 15 over 60, we kind of have the likelihood of being 25% or a probability of 0.25, right? So I'm just using this data that I have to get an idea about what those probabilities are. Okay? And we'll see some more examples of this, but this is the one that we'll use a lot. And then the last one's going to be subjective, right? So this one might seem like it's kind of, I don't know, BS, but we'll talk about why it could be useful, right? So subjective is where somebody who's an expert or somebody who has knowledge in that field kind of assigns the probabilities based off of their knowledge. So let's say a company is choosing a new CEO and they've got 4 candidates, right? Well, would I want to use the classical method here and say they all have the probability of 0.25 of being selected? Well, I don't know. Andy might have already bankrupted 4 companies. Whoops, where are we? There we are. Andy might have already bankrupted 4 or 5 companies, so maybe his probability of getting the job is very, very low. And maybe one of these individuals has had a lot of success, and so based off their resumes, I can get a pretty good idea about which CEO the company is going to hire, right? So I can't use the classical method because they all don't have an equal chance of getting the job. Can I use the empirical method? Well, this experiment would be I'd have to see a job opening where these were the 4 candidates, right? So if I'm looking at this, I don't have that. This is only the first time I've ever seen this happen. And so we don't know, or we can't assign probabilities based off the empirical method either. But because we know something about each one of these individuals and the job they're applying for, maybe an expert in that industry could assign who they think is more likely to get the job than others, right? Now, if you have any type of data, and the empirical method would likely be preferred to this subjective method, but this is a situation or a scenario where you can imagine sometimes we just have to use our knowledge to best assign these probabilities, okay? And then, if I can get going here, there we go. So welcome to Probability and Statistics, the class where everything's made up and the numbers don't matter, right? We just kind of subjectively assign these probabilities. We're going to try to avoid this, right? We're going to try to use the empirical method more often than not to look at some past outcomes that have occurred when we run this experiment to think about what the probabilities that it'll be certain outcomes in the future. Okay? So we'll go over some basic notation to just kind of set us up for how I'm going to start writing some of these things with probability. So the first thing we'll talk about is kind of the complement of an event. Okay? This is usually where I'd like to have something where I could write down. So let's say, we'll go through all of these and then I'll kind of give you an example. So the complement of an event we'll write as A with a superscript C. Okay? So what a complement means is if I think about event A as rolling a 1 or a 2 when I roll a dice, then a complement would be getting a 3, 4, 5, or 6, right? It's basically every other outcome that isn't in that event A you defined, okay? So if I define event A as rolling a 1 or a 2, a complement is rolling a 3, 4, 5, or 6, okay? The union of 2 events would be if I have 2 defined events, I'm saying, is the outcome in A or is it in B, right? So this kind of set symbol looks like a U, right? But what it's really saying is A union B. And what the union means is we can think about this as, is it in A or is it in B? So if you want to write like a little or above this or kind of next to this sign to remind you, that'd be good. A upside down U, or kind of, some people say if you like put a line through it, it looks like a A. So the intersection of A and B is it in A and is it in B? So it has to be in both of these events, right? In order for us to have kind of be looking at the intersection. And then kind of A with a straight line B, the way we read this is A given B. So given that B has already occurred, what are the likelihood or what are the chances or what's the probability it's an A? We'll kind of focus on this next week. But we'll kind of use these next week as well, but this, I'll give you a better explanation when we actually start thinking about probabilities. But we can do a Venn diagram, but I want to kind of, I think I can probably use Excel to type some numbers to give you an idea about what we're looking at here. Just do a blank file. And you could write these numbers down. I'm just doing this because I don't have a dot cam yet today. All right, so how do I want to define this? Let's think about, let's say my event A is that I see either a 2, a 3, or a 6. That's how I'm going to define event A. And then B is that I see a 3, a 4, or a 5. Okay? So that's my A and B. If I'm thinking about, well, how do I do this superscript? There should be an easy way to, forget it. I don't want to mess with this. So imagine that I'm doing I think I have to insert an equation, unfortunately. This is kind of a pain. So let me do equation A. This will help. All right, so there's my A complement, right? So what is my A complement going to be? If I think about what A complement is, it's everything that's not in A. So what would my A complement be? What are the only outcomes that aren't in A if I'm thinking about rolling a dice? 1, 4, and 5, right? Those are the other 3 possible values. Okay. What in the world just happened? Okay, let's try this again. Oh, it's because I'm putting an equal sign without text. Let's do, ignore that little thing, but it's going to allow us to get this entered in here, right? Yeah. So ignore that little period just because I needed to treat it as text, right? What if I wanted to do, I swear, copy, paste. What if I wanted to do B complement? So let's say down here, I'm going to do B complement, right? What would be in B complement? If 3, 4, and 5 are in B, basically the complement is what's not in B, but still a possible outcome. Just, you guys are scaring me. What numbers, if I roll a dice, aren't in B? Exactly, right? 1, 2, and 6. See, the people watching on Zoom are realizing how awkward it is. They're even trying to get the answers in, right? So 1, 2, and 6, okay? So that's how we would find complements. I think that's relatively easy, right? What if I wanted A union B, right? So this is going to be everything that's in A or it's in B, right? So if I'm thinking about what's in that set of possible outcomes, well, to be in A, I could see either a 2, a 3, or a 6, and to be in B, I could see a 3, a 4, or 5. So the union would basically be all of those numbers, right? So seeing a 2, a 3, a 4, a 5, or a 6. Right? Now notice if a number is repeated, it's only still one possible outcome. So to be in either A or in B, if I'm any one of these numbers, I'm going to be in one of these events. Did I add one there that doesn't belong? No, I didn't. We're good. Okay. What if I want a, I'm going to have to insert something here. So let's go down here. And I'm going to insert an equation. And I say, I want to look at A, oh, where's the sign? There it is, A intersection B. Okay. So if I'm thinking about A intersection B, what that's saying is what's in both of them. Okay. So what value or values is in both A and in B? Just 3. There's actually only one value, right? So that one's actually pretty easy. Okay. So 3 is the only outcome that's in both of these, right? Okay. So this is just kind of the way we want to start thinking about the complements, and we'll call these the union, or we use the terminology or, and this we can think about, this is my intersection, and we use that terminology of and. Okay? We're okay with this? All right, so a nice visual of this, right? Oops. There we go. Is if I think about here is event A and then here is event B, right? I kind of draw these as 2 circles. I'll use some Venn diagrams to get at some of these ideas, right? So A intersection B, or A and B, means it has to be in both of them. It'd be where those 2 circles overlap, okay? The union of 2 events is it could be in A or it could be in B, or hell, it could be in both, right? I don't care. It just has to be in one of them, one or the other. It can be in both, can be in just A, can be in just B, okay? So one way we'll start writing these probabilities is using something called a contingency table. So if I think about these events A and B, they also have their own complements, okay? So the way that we are going to decipher this contingency table, right, the way that we will read it, see these total columns, right? These represent the probabilities of the events on the row and column heading. So the probability that A occurs is 0.6. The probability A complement occurs, 0.4. Okay? Probability B complement occurs, go down to the total, 0.5. All right? So these totals kind of tell me the probabilities of the row and column headings. These top 4 left cells, and I'll probably say this quite a few times next week, but they all represent intersections. So this cell represents the intersection between whatever the row and column heading are. So this is the probability of A and B occurring, or the probability of A intersection B. Right? And this was kind of our upside down U, if you're thinking about how we write this. So the probability that A and B occur is 0.4. The probability that B complement and A complement occur would be 0.3. Right? Here we have another intersection. The probability that A and B complement occur is 0.2, right? So those top 4 left cells all represent the probabilities of intersections. The totals just represent the probabilities of whatever their row or column heading is, okay? Any questions on how we read that table? Okay, so that's how we read it. A lot of this I want to draw some stuff for, so we might have to punt a little bit. So I kind of already mentioned this is how we find the intersections. I'll come back to some of this next class. I'm going to skip ahead a little bit and show you something. Well, I guess I have it not for next week. I have 10 minutes, but I know if I try to explain this, it's not going to be as good as if I could draw some graphs. We'll have to say, we'll save that. We'll have to save all of this. So I'll go through this one. So I really want to hammer home this idea that those top 4 left cells represent intersections, right? So if I want to find the intersection of R1 and C1, what is the probability in that event, right, that I'm defining is that R1 and C1 occur. What's the probability of that occurring? If I go to this contingency table, I go to R1 and C1, that probability of the intersection should just be right here, right? So 0.4. So you should be able to identify intersections from this contingency table. And then if I ask you what's the probability of R2, you should be able to tell me that is also 0.4, right? So I don't think that's too bad. I think reading this contingency table should be relatively easy. There's a lot more we can do with this, and we can start to look at some of the probability laws. But without being able to draw freehand, I feel like I'm going to struggle. So I think next class, I'm going to have some pre-drawn things just in case that this .cam doesn't work again, because I'm starting to lose all faith. But I do want to go and try to give you a drawing I know I can do on here to kind of get at this idea of the complement. Okay, so this should be the last thing that we do today. So let's say I've got this experimental outcome space. So if we look at these Venn diagrams that we were looking at before, they all kind of have this big rectangle, and then the events, the circles were drawn in the middle, right? Well, what this rectangle represents is every possible outcome that I could see. This is like my experimental outcome space. So what should the area of this rectangle be? If I think about it, I could break it down into 4 even parts, right? So let's say this is event A, this is event B, C, and D, right? I have 4 different events, or let's just say 4 outcomes, right? What are if I added up the probabilities of those 4 outcomes, they have to add up to 1, right? So this experimental outcome space, kind of can think about it as the area is 1, right? Because if we added up the probability of every possible outcome, it should add up to 1. So we'll think about this experimental outcome space as 1. So we'll have this huge rectangle with an area of 1. It represents all the possible outcomes that we could see. Let's say, oh, come on. I then do, here's event A, right? So there's my event A. It includes, I don't know, some of the outcomes I could see. I don't know how many, but it includes some of them, right? It is a certain proportion of the overall possible outcomes I could see. So if this circle represents, oops, the probability that A occurs, right? So this circle is event A, so I could turn this into the probability that A occurs. Everything outside that circle, what would we actually call that? And I can't do the subscripts, or I don't want to, I'm not sure how to do the subscripts with this annotate tool. I don't think that it's possible, but as soon as I say that, someone will tell me that there is a way you can do it. So A complement, right? Or A superscript C that we were writing. So if I know the probability of A, what is the probability of, how could I find the probability of A complement? If this is the probability of A, then to get the remaining, well, if this entire space is 1, right, then the probability of A complement, we'll just call this, well, we'll write it out, is simply going to be 1 minus the probability of A, right? If I took this entire space and I subtracted out that circle that represented A, what I'm left with is A complement, right? So as soon as you tell me that the probability that A occurs is 0.2, I know the probability that A complement occurs is 0.8, right? Because it's just everything that's not an A. Sure enough, if I, everyone okay with this? Can I erase this or go change? We're okay? All right. Sure enough, if I look at these, here I've got the probability that B occurs is 0.5. So the probability B complement occurs is 1 minus that. So 1 minus 0.5 is 0.5. But notice the probability that A occurs is 0.6. So what's the probability that A complement occurs? Well, it would be 1 minus 0.6 or 0.4. Right? So, you know, these totals, the probability of A and its complement, should always add up to 1, right? And we had kind of that visual that I had just drawn up there that kind of shows us that, I think, a little bit cleaner. But next class, we'll think about how we use this contingency table to find things like unions, how we start to find some conditional probabilities, so A given B. Hopefully, like I said, I'll have the ability to draw a little bit easier because I know that it gets a little tricky, and I have a couple things that I know help show it a little bit differently, but it's going to be really hard to do with just that annotate tool. I'm going to need some kind of freehand ability. So I'll have that ready to go next class. Start trying to get as much of that Connect and Excel assignment done as you can by the end of, through the rest of this week. You have all of next week, but, you want to try to save that so you don't have last minute questions like next Thursday, before, shortly before it's due. Try to identify what those things that might kind of, cause you to get stuck are. So you could ask me early next week and we can get those settled. Okay? Any other questions for me before we get out of here? All right. Enjoy your weekend. I will see you guys on Tuesday.